In this lecture, let's talk about a concept that is known as fiber bundles. Now, fiber bundles, it's actually a concept that bridges your elementary general relativity and intermediate general relativity. Now, to have a fiber bundle, you can create those out of differentiable manifolds. So that is that you are supposed to have a space that is, well, it is locally, or it locally resembles a linear space, so that you can do or your calculus on that space. Now, to illustrate what is a fiber bundle, why not consider an example of this cylinder that I have drawn over here, this one, and I'm going to call this cylinder E. Now let's look at the cylinder a bit. Well, we have the cylinder and we cut out a circle on the cylinder that is S1. It's in a topological language, you call it S1. So it's a class of a sphere, right? And well, on the cylinder, every point on this cylinder, let's take an ordered pair A and B, right? So A and B are 2 points such that your A is or A belongs to S1 and B belongs to real or real line. Now you see these yellow and white lines that I have drawn over here, and well, they pass through these points P and Q. So white line is passing through Q and yellow line is passing through P. Now these lines are essentially what is called a fiber, right? Now let me explain. So let's well, before I go any further, first of all, you need to understand that you must have a differentiable manifold to have fiber bundles, right? As I have already mentioned before. So look at the cylinder. Is it a differentiable manifold? Well, you can make it a differentiable manifold if you make two assumptions. First of all is that it's an infinite cylinder, so it has to be infinite, so it has no ends, right? So that's the first assumption. Second assumption has to be that it's a hollow cylinder, right? So there's nothing inside of it. And if these two conditions are satisfied, then it implies that your cylinder is indeed a differentiable manifold. Right. Now, you have to note as well that your S1 is also a differentiable manifold. Your E, we have concluded, is a differentiable manifold. E is the cylinder, and your reals are also a differentiable manifold. So these, all three of them, are indeed differentiable manifolds. Now let's look at the cylinder. How do you create the cylinder? If you only look at S1 and R, how can I have a cylinder from this S1 and R? Now, this S1 is essentially also known as a base of the cylinder, and this R reals, this is what we call this fibers, right? So fibers is denoted by R for the cylinder, right? And the base for this cylinder is S1, right? So you could have this S1, you could have it anywhere, because obviously it's an infinite long cylinder, so there is no concept of having this S1 at a center or something. But yeah, so well, my question was, how can I have a cylinder from this fibers and base, right? So S1 and R. Well, it's very simple, and it's actually pretty straightforward to see that if I have this Cartesian product of S1 and R, I get my E. So that's the cylinder. Now let me explain a bit more. That is, say that, for example, or let's not take particular point, because every point on this E cylinder is associated to a particular base space and fiber, right? So you can see, if you look at this diagram, you can see that there is a base space S1 and some fiber coming out of that S1. So the fibers are, you could think of them as threads protruding out of a base, right? Now, well, you can see that your S1 is at a particular space, and for every point or different points on this cylinder, you would have, well, different fibers, so to speak. But, well, it is not general on a base space, but both the base space and fiber are required, right, to construct a cylinder, right, or to construct this E space, right? So therefore E is defined as the Cartesian product of S1 and R, which is then further equal to a set A, B, these points A, B, and these points A and B, well, I should also mention that the points B are, well, I wrote over here, these points B, they belong to the real line, right? So they could be, the point B could be anywhere on the real line, and S1, well, it could be in the range from, well, 0 to 2 pi, right? So coming back here, we can define the cylinder as a set of points A and B such that A belongs to S1 and B belongs to R. Now, this definition is a one-to-one correspondence with the geometric cylinder. Now, what that means is that this definition over here for a cylinder is actually the cylinder, right? Okay, so now let's look at this diagram over here again, and let's look at these 2 points, point P and point Q, right? Now, if you look at the fiber that is associated with Q, it is not generally the same as the fiber that is associated to this point P, right? You can see that there are two different, at 2 different locations, so to speak. But one way or another, they are indeed actually pretty similar, as the only difference is a different R attached to a different element of this S1, right? You can see that as these fibers are R, well, you can see that this is R at Q, and this yellow one is R at P, right? So we can simply consider a common fiber or a generic fiber for which every other fiber is just copies of that generic fiber, right? So we can define a single fiber and we can use that fiber and we can make copies of that to create all these other fibers, right? And that is what essentially makes a fiber bundle, right? So that is your fibers, or every let me write it down over here, your fiber are diffeomorphic, right? So what I mean is that the fiber at Q should be diffeomorphic to the fiber at P, and then essentially both of them should be diffeomorphic to the common or the generic fiber, right? Okay, now let's move a bit further and let's ask a question about the topology of everything that we have discussed so far, at least. So we know from topology, we know that if I have two topological space, say let's just consider this one again, S1 and R, right? I have these two topological spaces and I take the Cartesian product of these two space, then what I get is, again, I would get a topological space, right? But the condition is that both of these have to be topological, right? This one and this one, both of them should be topological space. Well, note over here that, it's a very important point, that this thing does not mean that if I have this E is equal to S1 Cartesian product with R, this does not give me E space as a topological space automatically. But we can give this space E, I can give it a topology, and that topology, let's say for example, I can give it a product topology. Now let's look at that. So if I want to give E a product topology, what that means is that or let's just define this, let's call it JE as the product topology, then JE will be a set of UI Cartesian product Vj such that UI, now what is UI? UI belongs to the product topology of S1 and Vj belongs to the product topology of R, right? Or the topology of R. Now, if this is defined for the set E, for the set E or as open sets for E, then you will have a topological space for E. Okay, well, I'm not going to choose such a topology for our particular case of fiber bundles right now. Why I discussed this? Well, it was just to answer the question that if we can even define a topology on this set E, right? So the answer is yes, we can, right? Now, well, note that given a point P on this cylinder, the point P in instead of calling it a cylinder, we can also call it the complete space E, right? So given a point P in this complete space E, it can always be assigned to a point in the base space. So you can look at this thing. So if I have this P over here, point P, I can assign it to this base space P if I go down, right? So for a cylinder, the example is, well, it is pretty straightforward to visualize it, right? So you have this point P, you can join it to the base of the cylinder. Likewise for point Q, you'll go up and you will join it to the base of the cylinder. Right. Now, again, what we want to do is we want to project down from P and project up from Q. So how we'll do that is, well, let me just put over here that you have to project down from P to locate a point on S1. Right, so we'll do that by, we'll create a map for that, right? So we have to create a map. Let me also write down what I'm going to do is that I have to project down from point P, and why we want to do that is simply because we can assign this point P in the base space, right? Because we can assign it to base space for our case, that is S1 circle. Right, okay, so yeah, so first step to do that is to create a map, and this map is called a projection map, right? Because we want to project down, so we'll just call it a projection map, and it is labeled as pi. Now let me just copy paste this image of this cylinder. I think I already have it on my clipboard. Let's see. Yeah, here it is. Okay, so let me just put this over here so you can have a look at it whenever you want while I'm doing this. So you'll define a map pi that takes your space E to base space. For our case, it is S1. Now, again, note over here, we know that E is defined as S1 Cartesian R, Cartesian product R. So this immediately implies that the map we would have of points A and B is equal to A, right? Because we know that if I give this point, the points A and B to this thing, you would go from this point B on this real line, and you would project it down to get a point A on this circle, because remember A belonged to S1. So this is the map that we need, right? This is the map that is required, because this is the map that if you give it the set AB, it would give you the point A on which this fiber is assigned to the base space S1, right? I hope it's clear. And let me also mention that this map, or it's actually pretty straightforward, it is a many to one map, right? So you have 2 points and it maps to a single point A. Right, perfect. Okay, so yeah, let me again mention why this map works is because A belongs to S1 and corresponds to any point such as, for example, you could take this point P, you could take this point Q, or you could have more, obviously, in this cylinder. Now, we also need to define the inverse map, and the inverse map, well, you can simply call it pi inverse, right? Of what? Well, you have this pi map that takes A and B and it gives you A. So inverse would be it takes A and it, well, let's see what it gives you, right? So first of all, we know that this inverse map should be a one-to-many map, right? Because the original map is a many-to-one map. So, well, what should it give you? Pi inverse of A should be what? right? It's also known as, the inverse map is also known as the pre-map, and this is what we want, basically, right? This is what we really want. Now, why do I say that? I say this because this pre-map will give you the fiber, right? It will give you the fibers. So if I have the inverse for this A on, that means that if I take a point A on this cylinder, then it would inverse map it to this real line or this fiber that is protruding out of that point. So for example, on the cylinder somewhere I had this thing was A. So if I give it, if I give this function or this map, inverse map, I give it A, it should give me the real line at A. And if you remember, I told you that this real line is known as the fiber, right? So that's what we essentially wanted, right? So yeah, that's a fiber. Now let's consider this point Q over here. Let's talk about this point Q. We will follow the same procedure that we just did right now. That is, we'll say that, well, let's say that Q is located at some points, let's call them C and D, right? Now, if Q is located at C and D, then if I take this map that we defined, so if I feed it C and D, it would throw out C, right? Following the exact same thing that we did over here, right? So if I had some points C and D, the map that is defined over here, right? So it takes E and it maps it to the base space for our case, which is S1. So immediately you can see from this thing that the inverse map or the pre-map of this C would be the real on C, point C, right? So this real at point C is your fiber at point C, and this was fiber at A. Perfect. Now note over here that this RC is not equal to RA, right? You can clearly see that because if you look at it visually, RA is this yellow line and RC, for example, if I had this point instead of Q, I have C over here. So RC is this white line, this one. And you can see that they are not equal. They are different sets. They are entirely different sets, right? But to have a fiber bundle, right? To have a fiber bundle, RC and RA, RC and RA must be diffeomorphic to each other. So let me explain. Diffeomorphic to each other and to the real line or in general. Now, if that is the case, then we say that we have a fiber bundle of RC and RA, and they are diffeomorphic to the generic bundle, that is, or generic fiber, generic fiber, which is the real line R. Now you can clearly see that this is the case. If you look at this, cylinder, right, you can see that RC and RA are indeed diffeomorphic to each other, and they are also diffeomorphic to a general line R in this space E. And this is a pretty trivial case, right? There are more sophisticated cases that are not much trivial and that are not so easily to be seen, just how you can see it for this case. For example, you could think of a sphere and now think of what could be the fibers in that sphere, what would be the base space, and so on, right? So yeah, that's a healthy exercise for you to do. But from this video, from this lecture, this part 1 of fiber bundles, the key point is that the inverse map has to be diffeomorphic to what we are calling the fiber. And only then you would have a fiber bundle, right? So let's end this lecture over here, and we'll continue talking about fiber bundles in further videos.